Looking now at the problems on page 45 and 46, just we'll point out a couple things, I guess. In problem 1, whoops there. In problem 1, please note that the units given on the acceleration are feet per second squared. So make sure you use acceleration of gravity in, well, if you use the 100 feet per second squared as the total acceleration in the first problem, then you can calculate the distance in feet from the kinematic formula, and then you can convert that distance to meters and miles. Okay, now in problem 2, the acceleration of gravity is the only thing that remains, and that's negative 9.8 meters per second squared. Right? So you want to use the right units. Use the right units. So if you use acceleration in the second problem as negative 9.8 meters per second squared, then make sure the velocity of the rocket at that point where the fuel runs out is also expressed in meters, because you have what you have is a rocket has been accelerated up for 20 seconds, so it's going to have some velocity at this point. For problem 2, that it becomes the initial velocity of the second problem, which then as it rises, that velocity decreases, so finally at the peak it's 0. So since we're using negative 9.8 in that second problem, make sure that the initial velocity given the rocket at that starting point is in meters per second as well. For example, we know from the problem that in the first problem, for 20 seconds accelerating at 100 feet per second squared means that the rocket will be traveling at 2,000 feet per second at the point where the fuel runs out. Okay, well that's fine. 2,000 feet per second is fine. Okay, 2,000 feet per second. But we need to convert to meters per second in order to use the numbers 9.8 as our acceleration of gravity. Okay, let's see. Problem number 3. I don't know why that's so small. Let's go back to 32. Problem number 3. The concept in problem number 3 is really that there is regardless of the speeds of the two drivers, the total distance traveled by the two drivers has to add up to 278, right? So if x p, which is Paul's distance he travels, and x a is Aaron's distance he travels, then that has to add up to 278. Okay? And since each one is traveling at constant speed, the distance they travel can be related through x equals v times t, right? Okay. Okay. I think I'll leave that one at that. Oh, let's see. Boom. On problem number 5, how shall we say this here? Do I have a prop here? I got a prop here. Here's my ball. Okay. Now, if I launch the ball horizontally, the problem says a ball is thrown horizontally off a bridge at 25 meters per second. If I launch the ball horizontally, I have not given it any upward or downward speed. So the only thing acting on it in the downward direction is gravity. So you can think of it as like a problem, like a one-dimensional vertical problem. It's the same as dropping the ball from rest. If I don't give it any vertical speed up or down, then the ball will drop and take the same amount of time to fall down as it would if I launched it sideways. It's just that the sideways motion adds a horizontal distance to its landing point, but it doesn't change the time it takes to fall. You try that with a couple of, take a couple of pins and very carefully release one, drop straight down, and toss the other one sideways at the same time, and listen, and they'll both hit the ground at the same time, just that they won't land at the same place. Okay? So the horizontal speed in that problem, 25 meters per second, doesn't matter, does it? Because all we're really interested in is the ball's got to fall. It's going to fall 25 meters down. So it starts with no velocity. Acceleration of gravity is the only thing acting on it. And we can calculate the time of flight. Okay. Similarly, in number 6, let's just write that down here. You might think number 6, we're throwing it at 37 degrees. That's not really a one-dimensional problem. But just continue to read the problem and ask yourself, wait a minute, I know how far the building is away, and I know how much time it took to strike the building. And the only way it got from where it was launched to the building was to have a horizontal speed. Well, I'll let you kind of finish that thought. Don't overthink these problems. Sometimes there's going to be data in the problem that you might think you have to use all the numbers in every problem. You don't. You think about what you need, what's important, and what's not important. Okay, as part of evaluating critical thinking type process. Okay. Let's see here. Just sort of glancing at some more of these problems. Number 10, the only thing about number 10 that might give you some pause is it's a high velocity. 400 meters per second is a high velocity, so that means that you're going to get a large acceleration as an answer, because this bullet traveling at 400 meters per second is going to stop in a distance. Where's my centimeters? There. In a distance of about that. That far. About that far. Okay. A little under half an inch. So the ball is going to come to a stop very quickly. Short distance, high velocity. Okay, so that means it's got to be a very high acceleration or deceleration, a negative acceleration. So we get a big number for answer to 10A. And then from the acceleration you get in 10A, you can figure out, okay, how much time. It had a high velocity, it stopped in a short distance, you're going to find it stopped in a very short amount of time. Okay. All right, let's take a look at Chapter 3. Chapter 3. On page 55 in Chapter 3, let's grab ourselves a new slide here. Yeah. Chapter 3, page 55. Okay, are the equations that are summarized in the x and y direction, and then in particular those are general, and we want to make them very specific to the case where we only have acceleration in the negative y direction. In this case 9.8, the acceleration here on Earth. So those equations then simplify down to the set given at the bottom of page 55, which I'll copy in right here. And maybe clean up a little bit because it doesn't take the subscript and superscript like I wish it would when I do that copy to PowerPoint. Let's see what we can do here quickly to clean these up a little bit. Okay, these equations describe the motion of an object undergoing two-dimensional kinematic motion under the influence of an acceleration in only the vertical direction. Okay? Only vertical acceleration. And in this case, the vertical acceleration is a 9.8 in the negative y direction. Since we have two directions to consider, that's why we have in particular subscripted the velocity and position with x and y symbols. I think I got them all there. There's one more. Sorry, one more. So when it says VOX, that would indicate the initial velocity in the horizontal direction. Okay. If it says VOY or VY, okay, that's obviously velocity in the y direction, either VO being original or VY being the velocity at some later time. Okay. Notice in the top equation here it tells us the distance x it travels is the starting velocity in the horizontal direction, VOX, times the time t. And VOX at all time is Vx at all time is the original horizontal velocity. So the fact is we're throwing an object at some angle, okay, but the only acceleration occurring is downward, so the horizontal part of that velocity doesn't change, but the vertical part of that velocity does change as a result of the acceleration of gravity. VOY and VOX are the components of the velocity described. Just want to scroll back here a little bit. Where would be a on page, well, here, let's just copy this. page 52, there was a problem example given which showed VOY and VOX. Okay. And of course, trying to put a symbol in here that is the theta for the angle, and the program doesn't like that. Let's see if we can change that font to theta. There we go. Okay. So, I need one more. Oh, there, VOX and VOY. Okay. So these two equations here define for us what VOX and VOY are. Those are the initial horizontal and vertical velocities given the angle theta and the initial launch velocity v0. Well, let's grab a problem that we could use here. Okay. Well, let's just take a look at number 1. Put number 1 right up here, okay? So what do we know in number 1? Well, we've been given V0 is 18 meters per second, and the angle is 41 degrees. Okay. All right, now, because we have the angle, we can take that and bring it down here and put it in our formula. Right? There and here. Okay. And we've got our V0. Same thing. We can take that and bring it down here and put it in there and put it in here. Okay. So we have our, that means, because we know V0 and theta, that means we know VOX and VOY. Right? So given that, okay, let's see what we can do. I don't know. Given that VOX, we can then come back up here and we can put that in here. And VOY, well, that'll go in to our formula. Well, a bunch of places, won't it? Right? Okay, so we can put that VOY, say, into this one here, or that one, or even the bottom one. Okay? So lots of different choices. Just have to ask the question, well, what did we want to know? Well, we want to know the time it takes to reach its highest point. So what do we know about the highest point? Okay. Vy equals 0. at the highest point, right? Vy equals 0. Okay. So, Vy equals 0. Well, here's an equation, the bottom one there on our list. Okay. We'll bold and underline that equation and make it all colorful. Okay. That equation, we could say 0 is Vy, and we know Voy because we calculated it right here. We put that in, and 2 times 9.8, that's negative 9.8. It's already in there because this is a downward acceleration. We could solve for y. Oh, wait a minute. Well, we weren't trying to solve for y. Well, that's all right. If we could solve for y, and maybe the question would be, how high did it go? Well, once we know how high it goes, we could then put that back into the previous equation right there. Okay, and solve for t. I like that color better, right? Because Voy is a known quantity, and 1/2 of 9.8 is 4.9. We have ourselves another little equation there where we know the y, and we've got the two terms, and well, it's quadratic, but that's all right. We know how to solve the quadratic equation from the quadratic formula. So that would be a pathway you could follow. Okay. All right, let me just glance through here. Sometimes people have questions on number 8. Number 8. Okay, number 8. Because the thing about number 8 is this. Let's take a look at what we have. A ball is thrown at an angle, right? So we've got 37 degrees. And we've got a distance of 55 meters and a height of 3.84 meters. Okay. Change that to a symbol. Okay. Now, inherent in this problem is the assumption of where we're starting, right? It doesn't say where we're starting, but what do we assume? Well, we have to assume we're starting at x0 equals y0 equals 0. Okay? So we know the location of the starting and ending points. We know the angle, and of course we know the acceleration is negative 9.8. We still have our list of equations from before. Matter of fact, I'm gonna grab that one, place that over here, and I'm gonna grab the first one there and bring that over here. Okay. All right. Those are two equations that I want to think about because, okay. Oh, and sometimes we don't include the starting point because it's generally assumed to be 0. But to be more explicit, let's actually put the starting point in both of our equations, y and x, so that it's clear that if the starting point isn't 0, then we would have a place to put it. Okay. So notice in this equation, the y equation, it says y is where it ends up. So that's 3.84. y0 is where it started at 0. Voy, we don't know all of that, but we have a way of calculating Voy and Vox. Remember our formula back here? Vo and y and Vox are given by the sine and cosine components of the initial velocity V0. And that's what we're looking for, the initial velocity. We do know the angle is 37. Okay, so if we go ahead and take that formula and bring it over here, paste it in. Okay. put in our theta. Okay. Put in our theta. So take that 37 there and bring it down and put it in our formula here and here. So then you can have an expression that says V0 sine 37, V0 cosine 37, right? Sine and cosine of 37, sine of 37 is 0.6 and cosine is 0.8. So we're going to have V0 times 0.8 and V0 times 0.6 for our OX and OY pieces. Then plug those into the previous two equations with the values of X and Y given, and you're going to end up with two equations that have two unknowns, right? You can end up with two equations involving T and V0. So solve by substitution. Solve by substitution. Okay. All right. Hope that helps. See you in the chat room on Tuesday night, and email me with any questions that you might have. Thanks.